session 1 of this STTP on Applied Computational Fluid Dynamics for of Mechanical Engineering Department, AD Patel Institute of Technology, a constituent college of CVM University. Today, for this session, our expert is Dr. S Mathpati sir. So I welcome sir, and now I will ask Dr. Mitesh Shah sir to introduce our expert for this session. Over to Mitesh Shah sir.
Very good morning, sir.
Very good morning. Good morning
Sir,
to all.
yes, sir. It's my pleasure and privilege to introduce Dr. S Mathpati, sir. And on 4th day of AICT sponsored faculty development program on the computational fluid dynamics for engineers. I would like to introduce Professor S Mathpati. Professor S Mathpati did his BTech, MTech and PhD from the Institute of Chemical Technology, Mumbai. Institute of Chemical Technology is world-renowned institutions, academic institutions, imparting knowledge in the chemical engineering and allied branches. Professor S Mathpati, awards and honors if you see, then he received Sir Mokshagundam Vishweshwarya Award in Engineering in 2019 by Mumbai Vigyan Parishad under Chemical Engineering category in 2019. He also received I&AC Research 2017 class of influential researchers who are early in their careers, less than 10 years into their independent research career. Based on the quality and impact of the research, this award he received in 2017. He was also the finalist in the INA Young Engineer Award in 2017. K.H. Garada Best PhD Thesis Award in 2011 he received. Currently, if you see, then he is working as an associate professor in Department of Chemical Engineering at the ICT Mumbai. His international and research experience, if we see, then 4 months at University of California at Santa Barbara, USA, where he studied about the PIV study of mass transfer mechanisms at seawater interface. This experience he received during June 2008 to September 2008. If we see the teaching experience of Professor S Mathpati, then he has already finished his 11 years, and during these 11 years, many courses he taught, and out of that, few of them are design of multiphase reactors, bioreactor design and control, chemical engineering laboratory, process transport phenomena. His research experience is almost 13 years, where he has worked in the area of computational fluid dynamics mainly, experimental fluid dynamics, design of multiphase reactors, process modeling and simulation, high temperature corrosion, application of liquid jets in chemical processing, hydrodynamics of packed and fluidized bed. He has guided 15 MTech students and 4 MTech students are currently working under him, and he has guided 3 PhD students. They have already completed their PhD and 8 students are working currently under him. He is having many publications in the various journals as well as conferences. The total number of publications on his names are 38. Sir, it's really a matter of pleasure for us to have with us, and I am very much sure that we will gain certain things after the end of these sessions. Thank you very much. Sir, now I request you to start your session.
Yeah, thank you. Thank you for this nice introduction. And very good morning to everyone. And today we are going to discuss about the applications of computational fluid dynamics in multi-phase flows. I hope the screen is visible.
Yes, sir, it's visible.
Yeah, thank you. So I would like to first thank Mechanical Engineering Department of A.D. Patel Institute of Technology for inviting me to have an interaction with all of you in the area of computational fluid dynamics. So today's talk is related to computational fluid dynamics of multi-phase systems, and I'll take a few case studies from chemical engineering. But when you see those case studies are more or less chemical and mechanical engineering of that type. So just before I begin with the technical talk, I'll just give a brief background about our institute. So our institute is established in 1933, and it is a state government university. We received deemed status in 2008, and our institute has NAC rating of A++, and our institute's NIRF ranking is also within top 50. The recent ATL ranking related to innovation practices, our institute is ranked 1 in government aided universities. And based on the performance, our institute has a category 1 status from MHRD UGC. In terms of the world ranking as well, our institute is one of the top rated institutes in Asia. So QS ranking, Asia ranking is 152, and Times Higher Education ranking is 92. So we have established in the year 1933, and recently in 2018, we have two more off campuses. One is in Bhubaneswar, Odisha, and another one is in Maharashtra itself in Marathwada, Jalna. Our institute has different programs which are there, and there are 9 undergraduate, 18 postgraduate programs, 29 PhD programs are there, and similar programs also run in Bhubaneswar and Jalna. And I would like to say that although it is mainly a chemical and allied technology institute, we also have a department of general engineering in which we have allied faculty members in civil engineering, electrical engineering, mechanical engineering as well. And we do have PhD programs in these areas as well. So our institute provides PhDs in the area of mechanical engineering, electrical engineering, civil engineering, even agrochemical engineering. So there are many PhD programs are available, and these programs have full-time PhD students who are supported through certain national fellowships as well as some industry support. And we also take faculty members from different institutes for the PhD under teacher scheme, and they get registered with one of the faculty, and their research work is done in the vacations or in their home institute or by coming on the weekends to the institute. So we do have PhD programs in mechanical, electrical, and civil as well. So this is a brief background about our institute. For more details, you can visit our website. So let us come to the topic. So today we are going to discuss about the CFD application in multi-phase flows, and we are already on the 4th day of this particular workshop. So all of you know what is computational fluid dynamics and its applications as well. I'll just briefly start with saying that a computational fluid dynamics is a study of fluid flow, heat transfer, and if you want to do some multi physics type of problems, then you can also incorporate chemical reactions, some surface activity like interfacial tensions. So there can be many complexities that can be added into a CFD framework. Why CFD is popular? Because it is a numerical experiment that we are performing, so there is no need to have a hardware infrastructure, and having a hardware infrastructure, doing experiments, it is going to be time as well as economically, it is not a cheaper option to conduct experiments. So a CFD can be a very promising alternative tool to reduce the number of experiments. So we cannot say that experiments can be completely avoided just because of the complexities in the fluid flow systems. And CFD has progressed over last few decades, and thanks to the advances in the supercomputing and the numerical schemes. Without improvements in supercomputing, the CFD field could not have been progressed to the extent which is now in the present day. So CFD helps us for better visualization and understanding of the design of the equipments. We have certain intuitions about how the equipment is going to perform. CFD only helps us to improve our confidence as well as gives a detailed mapping of the flow field in the domain, and which will help us for further optimization of such systems. Any validated CFD model can really help us in terms of improving the efficiency. So when I say improving the efficiency, it will help us to shorten the product design time scale. And in chemical engineering, it is also very useful to simulate the safety and accidental scenarios. In chemical engineering, computational fluid dynamics is mainly used for flow problems such as distribution of liquid in a reactor or a network of piping systems, understanding the pressure drops in the system, evaluating and quantifying the drag forces, then the non-idealities in the system. There might be certain zones which are not at all moving. If you consider a flow past a backward step, a very simplified flow, then the wake or the backside of the step, you can see there is a swirling flow, and in the middle and at the corner, there can be a stagnant zone which is not at all getting mixed with the bulk of the flow. There can be flow situations such as channeling and residence time distribution. So you consider a column packed with certain packing or some beads or something else, and if you put a liquid or a gas in that, our expectation is the entire amount whatever you have added as a pulse, it should come out as a pulse at the end of the column. So there is should not be any non-ideality in the system. But any real life system with a finite viscosity, when you add a pulse, it will come like a Gaussian curve. So there is a spread. So quantification of such spreads is very essential in reliable design of equipments. Then it can also handle reactive systems, particle dynamics. Now the particle dynamics can be a flow through a hopper or some filtration equipment, or if we are doing some drying of certain products, some granular products. So it can be from the area of agrochemicals, agro products, or it can be even the pharmaceutical tablets. So the range in chemical and allied technology of fluid flow issues is very wide, and CFD has contributed significantly in improvement over last couple of decades. So we can also solve for heat and mass transfer in the systems and understanding the mixing intensities and concentration profiling. So there can be different type of multiphase systems. It can be just a liquid system, for example water and kerosene, so they are not miscible with each other, and I want to do some extraction from one phase to another phase, so it is a liquid type of a system. There can be gas liquid systems, so two phase flow in the pipelines, so it is a gas liquid system. Then there are certain equipments in refineries and petrochemical complexes as well as fine chemicals which involve suspension of solid catalyst particle. Whenever solid catalyst particle is suspended, then we get improved performance from the equipment. So suspension of solid is one more aspect. Then gas solid systems, gasifiers, fluidized bed systems are gas solid systems. Another is gas liquid liquid systems. So again, it is some kind of a reaction system which is used in chemical engineering. When we do any CFD modeling, we essentially do it in 3 steps. The first is the pre-processing step, in which we define our computational domain. So any particular task which is assigned to us, we make certain assumptions, and based on the assumptions and the required details from the flow field, we decide the boundary of our domain. For example, I am working on a gasification system, and it is a circulating fluidized bed gasifier. So my domain extent will be just the circulating fluidized bed gasifier. In that, I am not going to account for the compressor which is giving the gas into the system, as well as the pneumatic transport of solids which is putting the solids in my system. So my focus is only on the gasifier equipment. So that is how we decide our geometry. Then we decompose our geometry into multiple grids. So that is the grid generation stage. Then we give the boundary conditions as well as decide the physical and chemical phenomena to be modeled in the system. So all these activities may take about 20 to 50% of your project time. The next step, which is more time consuming, is once you have taken all these decisions, then the computer has to solve those equations. Now the partial differential equations are converted into algebraic equations when we are doing computational fluid dynamics, and those equations are solved using iterative methods. So these iterative methods actually take up a lot of time, and after the solving stage is completed and you have a converged result with you, what you have only is pressure, velocities, temperature, and concentration at every grid point in the domain. But that is not what you wanted to communicate to your project fellows or to the people who are going to implement the solution. You have to process this velocity, pressure, temperature, raw data into more meaningful way. More meaningful way can be the quantification in terms of pressure drop. It can be quantification in terms of the heat transfer coefficient, mass transfer coefficient. It can be just the streamlines, how they are moving, whether there is any boundary layer separation, how much drag is being offered. So all these things are done in the post processing step, which is about again 20 to 30% of your project time. So as we have discussed that there can be different type of multi-phase systems, and in chemical engineering you can see various equipments are being used. It can be a reactor or a distillation column, or it can be a boiling system, or it is a vapor compression system. So there are many systems in chemical engineering and chemical industry which essentially involve the multi-phase contacting. So these systems need to be designed appropriately in a safer manner so that we can have consistent product quality, as well as we can have more throughput from such equipments. All the multi-phase flow systems have different flow regimes based on the properties of the gas and the solid and liquid phase, as well as the operating conditions. So if you consider a gas solid flow, if you have a very low gas velocity through the bed, then it is just a fixed or a packed bed type of a system. If you slowly increase the velocity, you will see the gas bubbles coming out from the system. If you further increase the velocity, rather than bubbles, there are slugs which are moving in the system. If you further increase the gas velocity, then you enter into turbulent as well as fast fluidization system. If you go to the other extreme, then the particles rather remaining in the system, they just get pneumatically conveyed with the gas phase. So gas has sufficient momentum to take away all the particles from the system. So we need to understand exactly under which flow regime we are operating, and whether operation under that flow regime is giving me benefit in terms of the improved transport phenomena. The another system is gas liquid flow. Again, there are different flow regimes like bubble flow, slug flow. There can be a stratified flow, dispersed flow. And based on the flow conditions and the material properties, you can get into various flow regimes. And all these flow regimes have completely different pressure drop characteristics, as well as their contribution to overall heat and mass transfer is also different. So I'll just skip this slurry system. So what are the various ways by which multiphase systems are modeled in computational fluid dynamics? The primitive way of handling multiphase systems is using empirical correlation. Consider I am trying to design a fluidized bed system. So to design a fluidized bed system, I will use the Argand's equation and apply the force balance in terms of the weight and the pressure drop, and then I derive the equation for minimum fluidization velocity. Once I derive the equation for minimum fluidization velocity, I will decide my operating velocity as 2 or 3 times the minimum fluidization velocity. Based on the velocity decision and the total flow rate we are handling, we will get the diameter of the column. Then based on the bed expansion characteristics and certain extra height, we decide what is going to be my height of this fluidized bed reactor. So this is an empirical way of dealing with this problem. Another is when there is going to be a gas which is going to fluidize my particles. So how the gas bubbles or slugs are moving in the system. So I want to track the interface between the solid and gas. So this interface tracking is done through a method called as volume of fluid method. Now this volume of fluid method will try to capture the interface between the gas and solid, and tracking the interface would demand very fine grid and very slow time stepping. So a simulation using volume of fluid method can give you very good information about the system, but the only problem is it may take couple of years to solve for an industrial scale reactor. So that is not the promising time scale that we want. Hence, we do some approximations about the system, and these approximations can be based on the percent of solid concentration in the system. Now, there are two extremes. One is you are handling a dilute system. Another extreme is you have a dense bed system. If you have a dense bed system, then what you can do is for the gas phase, you solve the Navier-Stokes equation, and for the solid phase, you solve the Newton's law. So what you are doing is you are tracking each and every individual particle in the domain, and tracking every individual particle and solving the gas phase as a continuum is a Lagrangian type of approach. Again, this is limited to several thousands to few million particles. Beyond that, it is not possible to have these systems used for the industrial applications. But any industrial scale system may have billions of particles. So again, this Lagrangian simulation has a limitation in terms of the computational power. So further simplification in the system is using an Eulerian framework in which you consider even the solid phase is going to act as a continuum phase. So it is also going to behave very similar to your gas phase or the fluid phase. Only thing is you are going to account for its hydrodynamics in terms of the modified drag coefficients and drag formulations and the modified viscosities of the system. So in Eulerian framework, there are two methods: algebraic slip model which is a simple model where you consider that whatever solid gas system you have is a mixture, and you solve the equations, transport equations for the mixture. Another way is, rather than considering as a mixture, you can solve for independent phases, and you apply the Navier-Stokes formulation to gas phase as well as solid phase, and you solve the system. And the interaction between these two phases is accounted through an appropriate drag model. So Eulerian-Eulerian framework is mainly used in most of the CFD multiphase applications, and its features are you are using a single pressure field for both the phases or any number of phases that you have in the system. So you don't define pressure for solid phase and the gas phase separately. You only have different velocities variables for gas as well as solid, but pressure is common. You use interface drag formulations, and in few cases you may also want to include the virtual mass effect and the lift forces. In case of, let's say, gas liquid system, the gas bubbles can get drifted in the radial direction as well, and this drifting is actually due to the lift force. And whenever these bubbles are moving upwards in their wake, that is the backside of these bubbles, they also get some liquid attached, and this liquid wake is also moving with the bubble. So under such gas liquid systems, these forces are important. Then you can also add additional complexities, such as if you have species transport or you have some reactions, those are taking place, and you solve the system. Once you solve these systems based on the velocity pressure information, you can get the design parameters such as heat and mass transfer coefficients. If the system is turbulent, then you also add the turbulence equations in addition to continuity and momentum equation. The another extreme is Eulerian-Lagrangian framework, in which the continuous phase is solved using Eulerian framework and the dispersed phase is solved using Lagrangian framework. And you may incorporate particle-particle interaction as well in this. And another thing is two-way coupling. So you consider the effect of continuous phase on the dispersion of the particle phase, but it may happen that the particle phase may also be contributing to the momentum of the continuous, that is gas phase. So if you consider the momentum effects in both the direction, then it is called as a two-way coupling. Otherwise it is just a one-way coupling. In case of VOF, what you do is you consider that both the phases are not penetrating in each other, and you solve an equation, additional equation, which tracks the interface of the continuous and dispersed phase. So VOF solves single set of momentum equations, but it solves an additional equation which is related to the interface. So if epsilon k is 0 in a particular cell, it means only one fluid is there. If epsilon k is 1, then the other fluid is there. And if it is between 0 to 1, then both the phases are present in that particular cell. So you solve for each and every cell in the domain, whether gas is present, liquid is present, or both are present. If both are present, what is the proportion? And based on that, you track the interface. So typical VOF problems which are there are jet breakup type of problems, the motion of large bubbles, because large bubbles can oscillate, they have elliptical and cap like shapes, and if there is significant liquid velocity as well, then there can be breakup of those bubbles. So there is lot of things those are happening at the interface, and this is the interface from which the mass transfer is going to take place, and hence it is really necessary to understand impact and contribution of such motions on the overall rate of mass transfer. Now there are certain limitations as well, which we will discuss when we take the actual case studies. So let us start with our first case study of solid gas fluidized bed system. So the fluidized beds are widely used for gasification of coal, biomass, etc. The gasification technology has recently been very popular just because it helps you to handle the pollution. So if you try to burn biomass or coal, then direct burning is going to be inefficient because it is going to be a partial burning, and it is going to release carbon monoxide as well as other toxic gases which are present based on the constitution of the material that you are using for burning. So rather than burning these things, if we gasify them, so in gasification we form CO and hydrogen mainly, and there will be certain extent of CO2 as well. So this CO and hydrogen are very useful either in terms of a fuel itself, or it is also useful to produce other chemicals. So there are many chemicals that one can produce using a gasified product, that is syngas. So you can do ethanol production, then you can do Fischer-Tropsch synthesis, you can go to naphtha, gasoline. So any of the refinery product that you get from the crude oil can also be obtained using a syngas chemistry. That is why this syngas chemistry and gasification is very popular, and large scale industries are trying to have such technologies. To have this gasification, there are various equipment designs. A simplest design is a circulating fluidized bed. There are modified designs such as dual bed gasifiers and other types are there. There is a upflow type of a gasifier, downflow type of a gasifier, crossflow type of a gasifier. So many designs are available, and all the designs have certain advantages as well as disadvantages. In case of gasification, there are different chemistries that take place. If you take a biomass gasification, the first step is the release of volatile gases. Now what are these volatile gases? It can be water itself, which is present in the biomass, and certain other volatile gases which might be there. So first step is drying and pyrolysis. So once you dry and pyrolyze, then you get char, tar and volatile gases. In the second step, whatever char and tar is available, it can get oxidized to form CO2 as well as CO. Then the carbon from the char also gets reacted with the steam which you are going to add in the system, and it is going to give you carbon monoxide plus hydrogen. Other chemistries can also provide you with methane. The CO and H2O can react to form CO2H2. So essentially what all these reaction schemes suggest is after gasification, you are going to get carbon monoxide, hydrogen, CO2, methane, and certain other gases based on the content of the biomass. Now let us see a design of dual bed gasifier, and we are going to do a CFD analysis of this particular system itself at a pilot scale. So a dual fluidized bed gasifier is energy efficient because the combustion zone and gasification zone are separated. Any gasification product is going to be containing CO2, CO, hydrogen, but the CO2 is as such not useful in the applications that we have. So we do not want to dilute our carbon monoxide hydrogen stream with CO2. These gasification reactions happen at high temperature. So in order to provide this high temperature, we have to do certain burning of the fuel. So a dual fluidized bed gasifier, what it does is the burning part is done in a separate column, which is just like a fast fluidized bed type of a system. So there is a riser type of a system available here. And what you have is a heat carrier solid material from the gaseous gasifier zone comes to the combustion zone. There is some combustion takes place. The combustion gases provide heat to the heat carrier material like silica. This silica particle again go back to the gasifier, and their heat is utilized for the gasification of biomass, and from the top you get the gasified products in this particular system. So this is a schematic diagram of a dual fluidized bed gasifier. The red portion is just like a entrained flow system where the heat carrying material like silica comes and it moves fast, and the residence time may be just few seconds in this, and it takes the heat from the combustion. Then the combustion products, gases, and the silica particle come at the top. Then there is a cyclone separator. So flue gas, which is mainly going to contain CO2, water, etc., goes out of the system, and these hot solid particles fall through this hopper into the gasifier zone. This gasifier is also in a state of fluidization, and it receives the heat from the silica particles, and the gasification takes place. This is how the circulations are maintained. And while circulations are maintained, this loop seal arrangement is very important, because loop seal avoids the biomass going towards the combustion zone, as well as it avoids the combustion gases directly entering into the gasifier zone. So it is just like a mechanical wall which we have in the system, and it is actually controlled by manipulating the velocities in the gasifier, supply chamber, and recycle chamber. So there are many optimization variables for this problem, and doing actual prototype studies for all the combinations is going to be very expensive. So it is necessary to validate a particular CFD model and then use that CFD model for further optimization. So this is the actual cold flow prototype we have in our lab, and the prototype is essentially for validating the CFD simulation. So the validation of CFD simulation has been done based on the pressure profiles by putting in the pressure sensors at regular height, as well as the solid circulation rates which are obtained by manipulating all the gas flow rates. So here you can see the actual operation of this gasifier. This is the gasifier zone, and at present no gasifier material is added. This is the heat transfer material, which is silica particles which we have in the system, and this is the connection coming from the combustion zone. So you can see solid particles are falling in this particular zone. Then near the loop seal, the material is coming in. From there, it is going to our combustion zone, which is just like a fast fluidized bed system. So this is how a material solid circulation is established in the system by manipulating the gas velocities. So there is no wall which we are opening or closing. It is just the action of the gas flow rates which is helping us to establish this circulation rate. So this is going to be a very complex phenomena to be captured by CFD, and hence the validation is very essential. So various experiments were done, and the data is collected. All this data is used for the validation of the CFD model. Now, if I decide to go ahead with the first type of modeling, just using the correlations and designing the system, but you can see the problem what we have by doing that. In literature, there are almost 15 different correlations for prediction of minimum fluidization velocity, and these correlations are predicting the minimum fluidization velocity from 0.1 to 0.4. So almost 300-400% error is there in terms of the correlation predictions for designing the system. So this much deviation or error is not acceptable in our engineering practices, and hence we go towards doing the computational fluid dynamics. So correlation based methodology of designing the system may not adequately work for this type of problem. So as a first step, we had decided the geometry for the simulation. So the geometry for the simulation is all these faces, the cross-sectional face at the bottom, these two faces, and this gasifier zone bottom surface cross-sectional area, they are the velocity inlet. This particular cyclone separator top is the outlet for the gas, and solid is in the state of batch mode, which is circulating in the system. So various boundary conditions for the system are also given here. In this case, the number of grid points which are used is about 15 lakh grid points are used. And this is done in a Eulerian-Eulerian framework, which means you are solving for both the phases. So equation of continuity and momentum balance equations are written for each phase. Then you make a decision about what kind of a drag model you want to use in the system, and you may also check the sensitivity of drag model on the prediction. So I will not cover that in detail, but a drag model selection is also one of the tasks in doing multi-phase computational fluid dynamics. So for the present case, the drag model given by Gedasco was used, and for turbulence modeling, we had used standard K epsilon. So the first step in any computational fluid dynamic problem is check whether whatever grid resolution we are using, is it sufficient or not. So to check whether it is sufficient or not, you can either compare with the available experimental data or keep on making the grid resolution fine till the point that the two different simulations having different grid sizes, the results overlap on each other. In this case, the grid spacing of 3.5, 4.5, 4 were used, and it was observed that if we have a grid size of about 3.5 mm, would be good in terms of the accuracy of this solution. Then we validated with respect to pressure profile at different velocities as well. So first validation was for grid independency. Second validation was in terms of changing the operating conditions and then comparing it with the experimental data. So we could observe about 20 to 30% error in the data, but which is within the engineering accuracy. So we accepted the solutions and went ahead for the further design. Then we estimated the holdup of solid phase and gas phase with respect to the riser height. So in a Eulerian framework, we could get very good visualization in the system. So I have shown a very small video here that how does the fluidization takes place in these systems. Next is the design parameter. In case of dual fluidized bed gasifiers, the major design variable is the solid circulation rate, SCR. So solid circulation rate is actually useful and important because these solids are moving to the combustion zone, taking up the heat and returning back to gasifier zone. So if you have a very good solid circulation rate, there would be more heat transfer that will take place, and it will help you for the faster gasification. So you can see that for different velocities, the solid circulation rates were fairly matching with the experimental data. So the model was found to be good for doing further design optimization. So the existing design of a dual fluidized bed gasifier which was studied, there could be a problem due to attrition of solid particles. Then there were certain problems in terms of the cyclone not capturing all the fine particles, and that was going with the gasification products. If with the gasification products these fine particles go, typically after this gasifier you will try to pressurize the gasified products using some compressor and then use it for further applications or transport it to somewhere else. So any particle going towards the turbines is not a good idea, and hence it is supposed to be avoided. So there has to be certain design optimization which is essential in all this. So there are two different designs of dual fluidized bed gasifiers which we evaluated, and these two designs had modification in terms of the main gasifier geometry as well as certain modifications near the cyclone separator. So these designs have been now optimized and certain recommendations have been done from those designs because it was a validated model and the solid capturing at the top. So this particular portion, this design has been validated just by doing a Lagrangian simulation for the cyclone separator, which I have not covered here. But this part is independently modeled using Lagrangian simulation and optimized. And the loop seal arrangement has been optimized using the Eulerian-Eulerian simulation frameworks. So another design which I want to discuss is now the next design I will just quickly rush through and then move towards the VOF type of validations. So another design, this is a part of our collaboration project with BARC. BARC is actively working with a research group in France on International Thermonuclear Experimental Reactor. This is a fusion reactor technology, and in this reaction system, lithium titanate particles are used, and these lithium titanate particles are used for generation of tritium. And it is proposed that a packed bed or a fluidized bed system with lithium titanate particles are to be used for thermal blanket modeling. So the heat extraction is very important and it is being done using lithium titanate particles, and these particles can be in packed or fluidized bed condition. But these particles are typically of Geldart B type of system, and fluidizing them is very difficult. If I have a packed bed instead of a fluidized bed, then a packed bed is not a good heat transfer equipment, so the heat transfer rates will be low. So we are stuck in a problem that it is difficult to fluidize the particles of Geldart peak type of classification, and if we use the packed bed system, then the heat transfer might be limiting. Hence, a combination of both is being proposed, that you have a bed which is packed with larger particle, and in the interstices of these particles, we try to fluidize the fine particles. So you visualize there is a column which is filled with larger balls, and then you charge fine powder to that particular bed, and this fine powder is being fluidized by the incoming gas, which is helium gas, which is being proposed. So helium gas is going to fluidize these fine particles in the system. So again, a stepwise methodology would involve certain experiments in the lab scale, use that data for validation. But now here you can see that we have a system in which large particles are there. So while geometry generation itself, we have a column, we put large particles in that, we delete the volume occupied by the large particles, because we are not interested in the volume which is occupied by the large particle. What we are more interested is in the void space of large particles, how the small particles are getting fluidized. That is why you patch it. So we have patched the fine particles in this bed, and then with respect to different velocities, we fluidize this bed and then validated with the experimental data. So this is again a gas solid type of a system, but a completely different application area, as well as completely different way of geometry generation and simulation. Again, we validated with respect to pressure drop. Parametric studies were carried out. Then heat transfer aspects were also studied once we had validated this in terms of pressure drop characteristics. So heat was supplied near the wall using electrical heating, and what kind of a temperature profiles get developed in the system has been modeled. So this is a multi-phase system with heat transfer. So one more physics that has been added into this. So again, the volume fraction of air phase in the particle phase, how does it look? So this CFD tool is very helpful in terms of visualizing the system as well as quantification in terms of the design parameters such as pressure drops and heat transfers. You also get the temperature profile along the radius, and it will give you an indication of localized heat hotspots. If the localized hotspots are having certain safety concern, then you can also develop a new design to avoid such hotspots. Next is a solid liquid system. This is a typically used chemical engineering equipment, which is stirred tank, in which you want to suspend the solid particles in the system. It can also be a pharmaceutical application where you want to suspend the crystal particles in crystallizers, or you consider that you are extracting certain essential components from the herbal products. So you are doing some extraction of essential oils from certain herbal products. So what you are doing is a leaching operation. So again, it is a solid liquid operation. So there are multiple scenarios in which we encounter such kind of systems, and it is important to suspend the solid particles. To suspend the solid particles, we use agitators in the system, but the type of agitator, the rotation speed of agitation, how much is the clearance of agitator from the bottom, what should be the diameter of agitator. So there are many more design variables that one has to address for efficient design of this system. Again, if we go by the correlation based method, the correlation based method may not give us an accurate and reliable solution. It can be just a starting point to generate a geometry for CFD studies. A detailed work has been done by one of the collaborators in our group. Murthy et al. Has published that, and various type of impellers were compared in terms of their power consumption to do the same suspension application. If you use two different types of agitators like hydrofoils, then the power consumption is much less compared to using a disk turbine type of a impeller, which just indicates that there can be a significant saving in terms of energy if appropriate choice is made. So how do we do it? So suspension of solid particles, a nice framework has been provided by Professor V.V. Ranade from National Chemical Laboratory. He has actually quantified the suspension quality using the computational fluid dynamics by taking help of the statistical methods. So again, this is a multi-phase Eulerian simulation, and you estimate at every cross section what is the fraction of gas, liquid phase and solid phase, and based on those fractions you generate the standard deviation, and based on the standard deviation you decide whether you have uniform suspension, you have complete suspension, or suspension quality is not good. So let us go towards now the volume of fluid method. Do you want to ask any question about gas solid flows or the Eulerian framework, or should I continue with the VOF and complete the presentation and we can discuss?
Sir, let
Yes.
us first finish your part, and then if there is any questions, participants will straight away ask you.
Okay, sure. Okay.
Thank you.
So another way of modeling multiphase flows is the volume of fluid method. Now in our group, we had applied this VOF method for one of the interesting problems in chemical process equipments. You consider a pharma application in which you have carried out a reaction in some solvent like toluene. The reaction is over now, and you want to recover your solids by evaporating the solvent. So you give a heat through the jacket and the solvent vapors will start coming out. But the problem is, as the solvent amount in the reactor reduces, the effective area for heat transfer is also reducing just because the level is going down. So as the level goes down, the heat transfer also goes down, and this takes very long time to empty the reactor. There is one innovation which can be done is, instead of having just one impeller, we can add two pipes to the shaft. So you are connecting two pipes to the shaft, and the bottom part of the shaft is kept in such a way that it will always remain submerged in the liquid. So as these pipes start rotating, due to the pressure differential that is created, the liquid is going to get sucked in these pipes. It will flow and it will fall like a jet on the reactor wall. So even if your liquid volume is reducing in the reactor, your heat transfer area remains the same, just because you are creating a fine film of liquid on the wall of the reactor, and you get very significant improvement in terms of reducing the batch time. Now this phenomena of how the liquid is rising in this and how the jet is getting created and it falls on the wall, we need to do a volume of fluid simulation. So simple Eulerian framework may not be helpful to me, because I want to track how the jets are getting created and then hitting the wall. So to do that, again, we created a computational domain, and as we are tracking the interface, the grid resolution has to be very fine, and hence you can see near this pipe we have very good grid resolution on inside as well as the outside. So the first step again is grid independency. So various sizes of grids were used, and then decided that when the results become independent of grid size, that grid size was continued. So these are certain results. So we carried out experiments in terms of measuring the volumetric flow rate at different rotation speed, and those volumetric flow rates were compared with the computational fluid dynamics using VOF, and we got fairly good comparison between the experimental flow rates as well as the CFD flow rates, and you can see some of the results. So this is a pipe type of wall water system in which the liquid will rise in this, and how does it come out from the pipes. Another way is, rather than having just two pipes which are rotating, we can just put a cone. So there is a cone which is there in the system, and if when this cone rotates, there will be a liquid which will climb on the inside surface of this cone and fall out on the reactor wall. So this is a cone type of a wall waiter, and you can see that how the jet gets created on the top surface, and due to jet instability, the jet breaks and the droplets will start moving with that trajectory and hit the reactor wall. So this is how a volume of fluid simulation is useful to track the interface as well as the breakup of jets, such kind of phenomena. Another example is, just based on the curiosity we had to do this particular VOF simulation, we were carrying out anti-solvent crystallization. What is meant by anti-solvent crystallization is, you have your pharmaceutical product dissolved in some solvent, let's say methanol or ethanol, and the solubility will get affected if there is some water present in the system. So what you do is, you take a saturated solution of your API in some solvent and you contact that with the anti-solvent stream. So this is being done in this particular example using two counter opposed jets. So one jet was with API. For our experimental purpose, we had used NaCl solution in water as the saturated system and methanol as the anti-solvent. So as soon as they come together, there will be a dispersion zone, and in that dispersion zone, it will be a completely mixed system, and that completely mixed system will cause the precipitation. As the jet velocity increases, our expectation was that the crystal size will reduce, because more and more turbulence, more and more power dissipation will indicate finer and finer particles. But beyond certain velocity, rather than decreasing the particle size, we observed the increase in particle size. And that phenomena we wanted to understand, and hence we carried out this VOF simulation. So here you can see that with respect to time, we have carried out this VOF at lower velocity 0.75 meter per second. The jets were hardly hitting each other, they were just falling. Then if you take at 4 meter per second, the jets were hitting each other, and after they hit each other, then they were hitting the walls of the system, and after they hit the wall of the system, there is certain back mixing that was taking place, and this back mixing was giving higher particle size than expectation. So beyond certain velocities, the jet which were hitting each other, they created a disk, and that disk diameter was almost equivalent to the diameter of the chamber that we had used, and that induced some non-uniformity in the flow and back mixing and deteriorated the performance. So by doing these simulations and the understanding that we had obtained, we modified the chamber design and avoided such situations. So this is how the jets will interact with each other. So one jet is coming, the another jet is coming, and this is the zone in which they are intimately mixed with each other, and help us to have a very good homogeneous turbulence field, and hence we get a very narrow crystal size distribution. In pharma, it is important to achieve the size as well as the distribution has to be very narrow. So this kind of a equipment would be really useful to get that kind of performance. So again, the CFD results, physically we carried out experiment, understood the disk that is getting created, and did the CFD simulations and tried to match at least the qualitative observations in this. Then we will discuss about the Lagrangian simulation. Lagrangian simulation is the particle phase, rather than considering it as a continuum and applying Navier-Stokes equation, we apply the Newton's law and we track all the forces acting on the body and then track the trajectory of those particles or the droplets. So this particular study we had done in the recent lockdown about development of a sanitization tunnel, and the kind of nozzle that we were using was a two fluid nozzle. If we would have used a single fluid nozzle where we are going to spray the disinfectant solution, the consumption of disinfectant solution for getting the complete coverage was almost 10 times more than using a two fluid nozzle. A two fluid nozzle helps us in terms of getting very fine dispersion of liquid at lower liquid flow rate, because it is mainly using the momentum coming in with the gas phase to do the dispersion. So there is a gas liquid flow which is flowing through the nozzle, and due to which certain drop size distributions will get created, and the liquid consumption is extremely low compared to the actual consumption in standard single fluid nozzle designs. So we could create the dispersion. Now our objective was whether we are covering the entire surface area of the people who are walking in the system, whether I can have a single walkthrough system or the person has to come till the midway, take one or two rotations and then move out of the system, at what speed the person should walk, whether the normal speed of walking and once through will ensure almost complete disinfection. So all these were the objectives for the simulation. So we created a virtual CFD model for this and carried out simulations at various locations of these two fluid nozzle. In this simulation, we had taken a human model, CAD model, and on this CAD model, whatever the droplet flow is there in the system was evaluated, and we carried out this by taking multiple cross sectionals at head height, chest height, knee height, and how much surface coverage we can get at what kind of a flow rate of droplets. And then we optimize this particular system in terms of the total liquid that has to be consumed, as well as the speed which one has to maintain in the sanitizer tunnel. So this is how we had used a Lagrangian simulation framework to optimize this kind of a system. So let us conclude from this that multiphase flows are quite complex in nature. The CFD predictions can be improved by tuning the model parameter. I had not discussed more about tuning of the model parameters, which we typically do for gas solid systems in terms of evaluating various drag models and modifying their constant to get the good predictions with the experimental data. But that is an essential part of multiphase modeling. CFD provides very valuable insights into transport phenomena in the system, and it is a very promising tool for scale up of multiphase systems. I would like to acknowledge ANSYS for providing the software support for research in our institute. We have very long-term relationship with ANSYS for almost more than 3 decades now, and we have ANSYS licenses, and around 15 to 20 PhD students dedicatedly work in the area of computational fluid dynamics, and all of them have required licenses available for their work, as well as the high performance computing, and the technical support from ANSYS is also available as and when required. The computational facility is typically built using the funds that were available with the Department of Science and Technology and TechWeb grant. And the presentation which I had shown is based on the research work of various students working with me. Mr. Naresh Hansate, the first part, the gasifier system design. Aniket Wawal, the VOF simulations, impinging jet and wall wetter. Dr. Sandeep Gosavi and Shekhar Sawant, they actually worked in the airlift reactors as well as the packed fluidized bed systems. And the sanitizer tunnel work was done with the help of few PhD students working in the similar area, Mr. Ketan Desai, Tukaram Shinde, and Vikram Koprale. So Vikram Koprale is a mechanical engineer, and he is working in our institute as a part-time faculty as well as doing PhD. And his research project is also related to computational fluid dynamics and optimizing the heat transfer equipment designs. So he is working on solar thermal type of projects. So with this acknowledgement, I would like to thank you all for listening to this talk, and we can discuss if you have any questions now.
Sir, thank you very much. Really, your session was excellent. You had very nicely covered the DFB, Dual Fluidized Bed Gasification System, Packed Fluidized Bed Gasification System, pharma industries case studies also you mentioned.
Yes.
Sanitization tunnel also you very nicely simulated in the CFD. It was really interesting. I just wanted to know certain thing. In DFB, whatever syngas generated, are you cleaning and cooling that syngas or not? Is there any mechanisms you have kept?
No. In our system, so far we have only done cold flow studies.
Okay.
So it is just the silica and air, such kind of work we have done.
Okay.
Because the actual syngas related project activity is going to be very costly, because we have to account for the safety aspects as well, and it will require certain infrastructure in terms of handling such reactive systems, combustion systems at high temperature. The present bottleneck to apply for such projects in our institute is located in the heart of Maharashtra, Mumbai. So we just have 16-acre land, and the space is the constraint. So these kind of actual prototype activities we are planning to take in our Bhubaneswar campus, IOC supported, because that campus is supported by Indian Oil Corporation.
Correct.
So there we will have certain space available to build all these type of systems. But IIT Guwahati has very nice facility in terms of designing and operations and trials for such kind of activities.
Okay.
Yeah.
And have you carried out these simulations at a different equivalence ratio or something like that? Have you checked that parameter for the cold flow analysis?
Yes. We have done those, and we have also done Aspen simulations for accounting the actual reactions and optimizing the feed parameters and accounting for the kinetics and how it will be the impact on the syngas generation. So those kind of activities are done, but with a different platform altogether.
Correct. It was really nice insight you had given with the different multi-phase flow cases. So at least audience also, I'm pretty sure that they should understand which model has to be adopted for the solid liquid, solid gas or gas liquid conditions. Really good. I request audience, if any doubt will be there, they can ask either through chat box or directly also.
Good morning, sir. Can you hear me?
Yeah. You are audible.
Sir, my question is about bubbling fluidized bed gasification system for syngas generation.
Mhm.
Sir, syngas which we get from the cyclone separator has the Reynolds number of between 2000 to 4000. Then we can't say what the flow is. So how can we know that the flow laminar or turbulent of syngas there, and how CFD can help us?
Typically, the transition of flow regime from laminar to turbulent in the range of 2000 to 4000, this transition range is, if you see, it is mainly for flow through smooth pipes without any disturbances in the incoming fluid. For those kind of flow situations, we say that there is a transition from 2000 to 4000, and this critical Reynolds number will differ for different flow systems. Now, as we are talking about a multi-phase system where the gas as well as solids are present, then the turbulence in the system will start at very beginning stage. If you consider a particle falling in a fluid, so less than Reynolds number of 1, we call it as a Stokes law regime, and beyond Reynolds number of 100, we say that we have already entered into the turbulent conditions. So for these systems, the Reynolds particle Reynolds number is very important, and anything above 100 of particle Reynolds number will mean that it is a turbulent system, and one has to use a turbulence model. In addition to that, we also have a heat effect, and there is a thermal gradient in the system, and the density of gas is also significantly dependent on the temperature in the reactor, and this temperature change across the radius will also induce a natural convection in the system due to the density difference, and hence the flow will remain turbulent. So the question of whether to go for laminar type of a model in such systems, it is always better to deal with the turbulence. So it is good idea to use turbulence models to deal with such systems because of the complex flow situations, and the turbulence gets incepted at an early stage due to complex heat transfer behavior as well as the particle interactions.
And sir, how CFD can help for the calculations like for pressure drops and all the things?
Yeah, CFD is essentially very good to calculate pressure drops in the system because you are solving for the pressure as a variable. So whenever you want to estimate a pressure drop across certain length, what you do is in post processing you create cross sectional surfaces, and you get the surface average quantity pressure at both the planes. So the surface average pressure quantities difference is the pressure drop in the system.
Sir, actually, I am now in the final year of my BE mechanical, and I am now working in this project in my final year. So, sir, can I get this PPT for my reference?
Yes, you can write to me, and I'll share the most of the content of the PPT, only reducing certain part, which I will not be able to give you.
Okay, no problems.
Yeah, you just send me an email. I will share that with you.
Okay, sir.
Yeah, sure. Any other question?
Sir, you have shown a nuclear fusion reactor in which you have shown that we can use packed bed along with the fluidized bed.
Yes.
Sir, but in fusion, the major issue is the plasma confinement. So, if we use, say, fluidized bed over there, it will make it more difficult to, say, maintain that plasma confinement. So, how we can use CFD and ensure that that plasma will be confined in that fusion reactor?
Oh, okay. So that actually, this question actually goes beyond the project activity we were doing, and I don't know much about the other aspects of that reactor. So
Okay,
I
no
was just
issue, sir.
looking at this, but you can contact Professor or Mandal from BARC. He is a project lead from India who is
Okay,
interacting with the ITER group.
sure, sir.
Yeah,
Okay, thank you, sir.
yes.
Any other questions? So with this, sir, we have maintained this practice. Let us say any participant want to ask any further query, so they can write the same to me and I'll compile it and mail the same to you.
Okay, sure.
And as one of the participant has requested your PPT, so maybe whatever you are willing to share, you can share the same to me and I'll share it with all the participants who have registered for the same, right?
Okay, sure. So I'll share certain slides and I will share the publications which have come out of this. So you will get all the details from that publication file.
Yes, sir.
Okay, yeah.
So with this, I would like to thanks Mr. Dr. C. S. Mathpati sir. In spite of his very busy schedule, he has given us this opportunity to listen to him and the great work he has done in this field. With such a simple approach, he makes us understand things so well. I hope the participants must have get a benefit of the same. With this, I would like to thank you, sir, and thank you so much for sparing your valuable time.
Yeah, thank you.